Assalamu alaikum dear students, welcome to the online lecture on the Matlab simulation related to extended state observer based control of flexible joint system. So today we are going to discuss the controller presented or proposed in this paper. This is published in IEEE Transactions on Industrial Electronics in 2010. So this control method is a little bit old, so if you are like really interested in it, so you should be looking at not only this paper but also at the papers who have cited this paper, so that you get the latest information that is follow up on today's video. So as usual, we are not going to discuss the research paper in detail, but we will be focusing on the mathematical model and the controller, and we will be simulating the results that have been presented in the paper, basically reproducing the results that have been presented in the paper. So this paper discusses the feedback linearization based control along with the extended state observer. The idea is, the motivation is that feedback linearization cannot be implemented unless the full transformed state vector is available, and there are even if this transformation state transformation is available, even then the feedback linearization is prone to the uncertainties in the model. So to cater for that, the authors have proposed a method where they augment the feedback linearization controller with the extended state observer that estimates the uncertainties in the system. They have also done the experimentation and presented in the paper, but of course this video is not about experimentation but just the simulation of the results. The introduction section and this section 2 basically presents the mathematical model that we are interested in. These are the equations of motion, and this is the system where we have Q1 and Q2 are the link and motor angle. So Q1 is the link angle and Q2 is the motor angle, and you have I is the link inertia, J is the inertia of the motor, K is the spring stiffness, U is the input torque, M and L are the mass and the length of the link. So this is all the details about the physical system. Then they discuss the controller, for which they have assigned the state variable x1 is equal to q1, which is the link angle, and x2 is equal to the rate of change of link angle. Then x3 is motor angle, and rate of change of motor angle is x4, and so on. But then they convert this x1, x2, x3, x4 state variables using a diffeomorphic coordinate transformation, which the details are in the reference 5 and maybe in reference 23 as well. So these are the transformed state variables: z1 dot equals z2, z2 dot equals z3, z3 dot equals z4, and z4 dot equal some nonlinear function a plus b times u. And then a is this mgl over I into sine of z1 and z2 square minus k over j, and so on. And b is just k over I times j, which is probably a constant. And then these states z1, z2, z3 are basically link position, link velocity, acceleration and jerk respectively. And they have also presented the extended state observer for the system. So for implementing the extended state observer, they have basically introduced a new state variable, which is the equal to disturbance or uncertainties in the model. So they have used the technique that we have z1 up to zn are the state variables, but this variable zn plus 1, this is basically, if you look at the model here, zn plus 1 would correspond to this az nonlinear, so nonlinearity in the system model. So So instead of a z, we have z n plus 1, and we have included the dynamics of z n plus 1 into our model. So h will be the dynamics of the uncertainties. And then you have the state estimates z1 hat, z2 hat, and up to so on zn hat, zn plus 1 hat. So these are the dynamics of the estimator. So you can present all of this in as a linear model, z dot equal a z plus bu plus eh, where a matrix is given like this, b matrix is given like this, e matrix is given like this. So this is the linear approximation of the transformed state space model, and this is the linear representation of extended state observer. So the title extended state is because of this introduction of an extended state variable zn plus 1. So they have extended the state space model by adding additional state. That is why the title extended state observer. Otherwise it is just a simple it's very similar to Luenberger observer, if you know what Luenberger observer is. Otherwise I have another video about how to design the Luenberger observer, and how to design observer based compensator. Maybe I'll add the link of that video in the description of this video. Anyways, so feedback linearization controller plus extended state observer based controller is implemented in a way that we have 4 state variables, and then this is the equation for control. 1 over b naught is the b sub 0 or b sub o, b naught, you can call it anything. So this is the this is the known part of b, and there is unknown part of, so b is composed of so bu is equal to you can like so this is the disturbance is az plus delta bu, where delta bu has this known part b naught and unknown part, which you can call it anything, which is the difference between the known part and the actual value of the b. Which is delta b. So delta b is basically delta b and b naught. So that will be a complete description of this constant b in the model. So this is the control equation, which can also be written like this, because this disturbance is estimated with the 5th state of the observer. And we will be looking at the code relevant to this system, where we have this type of observer and the controller. We will be using the equation 16 in our code, and then we will be regenerating these results. And there are some parameter values also given in the paper, the value of mgl, the value of k, I, j, and then they have also presented how they select the poles of the controller and the observer. And then they have also presented what is the reference trajectory for the position of the joint. Okay, I think that's it. That's all about the paper, and now we can shift our focus on to the Matlab code related to the paper. So in order to write the Matlab code, you basically first you have to calculate the controller gains. So this is once again please feel free to pause the video here and take a screenshot and copy this code and run it on your own computer, so that you get a feeling of how this code works, and also you have some practice of Matlab coding related to control systems. So basically in this code, first of all, we write down the values of the constants that are given in the paper. This capital K is equal to 100, it's given here, and this capital J, capital I, and B naught is equal to K over I multiply by J. So I into J. Let me confirm this from the paper. So here so this is the B is equal to K over I multiplied by J, so this should be it. And then you have A matrix, B matrix, C matrix, and then so the way they calculate the poles or gain of the controller, it's mentioned down in the simulation section. If you go to the simulation section, they say that the controller gain Ki required in the equation 16 are obtained by placing the poles of this transfer function with a time constant of this TC value is 0.35. So first of all, what we do is we write the ABC matrices that are given in the paper. So ABC matrices are given in here. So if you go here, so these are the so these are the AB matrices and C matrices given here, and then we write them down, and then we convert them into transfer function like this: 1 over 1 plus TC over 4 times S, as presented here in the simulation section. Here 1 over so TC plus TC over 4 into S raised power 4. We need to find the poles. So you can use the Matlab command pole, POLE, to find the poles of this transfer function, which the poles of this transfer function are roots of this polynomial, and you can use these poles and into the place command. So when you are applying the place command, remember the original state space is 4 state variables, so you have to use the first 4 rows and first 4 columns of A, and B will be also 4 cross 1 matrix, and then place AB like 4 cross 4 part of AB, and P1 will be the value where you will be placing the poles. And then for observer, you can place the poles 1 over 1 plus T naught over 5 into S raised power 5, where T naught is TC by 3. So here I have this is TC 0.35 from the paper, T naught is TC by 3, and this is 1 over T naught by 5 raised power 5. So you can use here P2. So instead of P2, I have used these pole locations which are very close to what P2 is. It does not really matter much. You can use P2 or you can use these pole locations. The results, the gain will be very similar. So in order to apply the place command for observer gain, you have to use A transpose instead of A and C transpose instead of B in the place command. And once you calculate the gain, you have to take the transpose of the gain. So this is how you calculate the observer gain. So this file, all this file does is, if I run this file, so this file will calculate the observer gain and the controller gain. So this is the controller gain and this is the observer gain. So notice this observer gain has very high values, 10 raised to the power 8, because we are placing the poles very far away into the left half plane, minus 41, minus 42, and so on. But anyways, so these gain values are now going to be used in our function file. So this is the next file where we will be using these gain values. So I have copied these gain values already. So and these are the observer values, observer gain values. Notice this is like 1.3675 into 10 raised power 8. So these two values, Ks and the observer gain, these are calculated from this file, which is used to calculate the gains. And next we implement the model. So again, all the constant values and then we need to, this is I multiply by j, and then we have h is equal to, so the disturbance I have taken this to be equal to this h az. So I have you can make the disturbance equal to anything, but from reading this paper does not explicitly says that h is equal to az, but I figured that this is the most appropriate expression for a. So az is mgl over I sine of z1. So this is mgl over I sine of z1 is our first state variable x1, then x2 square minus k over j, and then minus mgl over I into cos of x1, and plus k over j is, this is k over j plus k over I multiplied by the third state variable, and so on. So this is the value of h that I have taken. This is what I have done on my own, so this is not explicitly written in the paper that h should be taken this way. Okay, so then we have these ABC, ABE matrices. These are given in the paper like here. Where is the, so we have, yeah, here in the after equation 11. So we have these matrices here, and then these gains we have calculated from the other file, and this is so z is first 5 state variables x1 x2 x3 x4 are z, and z hat is x6 x7 x8 x9 and x10. So there are total 10 state variables, 5 state variables of the extended state space, and 5 state variables of the estimator for that extended state space. Z1 is 30 sine t, the Z1 is the desirable value of Z1, which is Z1 star in the paper. So Z1 in the Matlab code is basically this Z1 star. So Z1 this value 30 sine t, this is the reference trajectory to be tracked by the state variable, the first state variable, which is x1 in our case in the Matlab code, and z1 in the paper. So this is z1 star, this is the derivative of z1 which is z2 star, this is z3 star and z4 star. So all of these, z2 is the derivative of z1. So derivative of sine is cos, the derivative of cos is minus sine, and derivative of minus sine is minus cos, and derivative of minus cos is. So this z4d is basically, if you go to the equation of the controller, so this is z4d is this z4 star dot. So this is the derivative of z4, desirable value of z4, and then r is basically the list of references, z1 star, z2 star, z3 star, z4 star. So r is basically, you can rewrite equation 16 like this. This is so this is equation 18 is the another form of equation 16, where you can write it like ks times, ks is the controller gain that we have calculated here, and r is basically the vector of the desirable values. Then this z hat is observer states, and then z4 star is this desirable value of z4, and then there is z5 sorry, z4 star dot is the derivative of the desirable value of z4. So this is the MATLAB file for writing the function of the dynamics and the control, feedback control. Also like in the end, dx1, the state dynamics is a times z plus b times u plus e times h, as is like this z dot is a times z plus b times u plus e times h, and the dynamics of the observer a times z hat plus b times u plus l times c times z minus z hat, and this is dx1 colon dx2. This is all 10 state variable. So this is the function file that captures the dynamics of the state space, extended state space, and the observer dynamics, and it also captures the desirable values of the state variables and their derivatives, and it also captures the control law that is from the paper. So notice that in our implementation or Matlab code, z4, so if you go to equation 18 here, this is z4 dot, z4 star dot, this is z4 star dot, which is here in the equation, and this x10 is basically z5 hat. So this is the fifth state of the observer. So x6, x7, x8, x9 and x10 are the 5 states of the observer. Among them the fifth one is x10. So this x10 is z5 hat. And then finally we go to the file where we call this function fleso. So see that this function is fleso. I have named it feedback linearization extended state observer, and then you can call it using ODE45 function, run it for 10 seconds, because they have we want to reproduce the results from this paper, so we need to use the same so they have run it for 0 to 10 seconds, and this is z1, z2, z3, and they have plotted the state variables, and we are hoping to get the same results. So this is like just we calculate the trajectory, then we plot the state variables z1, z2, z3, z4, z5 and z10. Z10 and z5 are, this is the x5 z5 and this is z5 hat. So here they have compared the actual and the estimated state of uncertainty. So z5 is the uncertainty. If you remember, the fifth state is the disturbance or uncertainty state. So once we run this, and the results are here. So this figure 5, this is the this is correspond to this figure E in the paper. You can see here this is quite similar, that the dotted red line is tracking the blue line. So the estimate of the uncertainty is quite close to the actual value of the uncertainty that we have chosen. This figure 4, this corresponds to this figure in the paper. You know, there is some transients and it's finally settles close to 0. And then there is this figure 3. Where is this one, figure 3? This corresponds to this figure. So this is the well, yeah. So we have not plotted the estimated value of z3. We can do that. So estimated value of z3 is x 5 6 7 in our case, I think so. Yeah, 5 will be z1 hat, x6 will be z2 hat, and x7 will be z3 hat. So we can plot here. We can, where we have plotted z3, we can write this control C, and with z3 we can write z x7. x7 is z3. So we can run this again and look at figure 3. Well, this is not quite similar to what we have here. Yeah, so we can see, we can try to actually compare the other states as well. But anyways, we will see if I will look into it if there is something wrong with the estimator code. But this is like this is Z2 and this is corresponding to this figure. And if you look at the Z1 trajectory, figure 1 presents Z1, which is this figure. So you can see here that there is almost perfect tracking of this dotted red line is the uh, reference signal, and the blue line is the actual. Let me confirm this. So actual is blue line and the reference signal 30 sin t, that is the dotted red line in figure 1. Okay, so this is the code that you can use to run the to implement the extended state observer and feedback linearization. uh, and I hope that this video was useful for you, and will continue to post more videos related to control systems theory and research papers related to different topics and applications of control systems. If you want to follow up on the upcoming videos, I would recommend that you subscribe to the channel and hit the bell icon so that you will know whenever I post a new video about any research paper. Thank you for watching this video, and once again at the end I would just make this Matlab code, which this is file number 1 where you calculate the gains. This is file number 2 where you implement the controller and the observer, and this is file number 3 where you basically you can plot the trajectories. Thank you very much. That's all for this video. Okay, sorry, I need to add a correction at the end of this video, because this x7, if you remember, if I run this file, this x7 and x3 did not agree. Well, there is a reason for that, because I did a little bit of mistake in calculating the number of states. So there are 5 states, and state number 6, 7, 8, 9 and 10 are the observer states. So state number 3 corresponds to state number 8, not state number 7. That was my mistake. So if I run this, if I make this state 7 equal to state 8 and compare with state 3, now if you look at figure 3, so the estimate is perfectly tracking the original value. So the estimator, there was nothing wrong in my code of estimator. Similarly, you can compare state 7 with state number 2. So if you copy this, control C, and paste this here, control V, and state number 7 basically corresponds to state number 2. So if you run this and then look at figure number 2, so you can see here there is a perfect tracking between the estimate of the state number 2, which is state number 7, and the actual state number 2 of the system. So this was one correction that I wanted to talk about at the end of this video. Thank you once again for watching this video, and hope you had some learning from this video.